Welcome everyone to the EBO webinar podcast series. My name is Aaron Smith and I'm joined as always by Nancy Bakeman. And we're really pleased to have Sarah Koch here today with Newport Partners. We've been spending a lot of focus over the past year on water efficiency and water issues, particularly across the Western United States. And then carbon has become a big topic. I was on a carbon panel this morning on behalf of EBA, and I know it's an issue facing builders. So what better topic could we have today than hot water innovations for decarbonization and our great partners over at Newport Partners presenting. So we do have a Q&A section open today. You can enter your questions there. You can enter them in the chat as well, and we'll present those to Sarah throughout her presentation today. Sarah, welcome. It's so great to have you here with everyone today.
Great. Thank you so much, Aaron. Yeah, so we're focusing mainly on how to decarbonize hot water. So I know there's all sorts of different carbon tied up with water purification and water scarcity and everything like that, but today we're talking about hot water. So first, we're going to take a little time looking at the why for decarbonizing hot water. So it's always good to step back and look at the big picture for why we're putting so much time and effort into this new, complex, pretty expensive technology often. And then after that, the majority of the webinar, we're going to cover the how. We're going to go through heat pump water heaters, which are the main hot water decarbonization strategy. And then we're going to cover a few other less common technologies and then discuss the challenges and opportunities associated with heat pump water heater, specifically implementation. So a question that I have gotten before is, will decarbonizing the United States really make a difference across the globe, considering everybody else's carbon emissions? And the answer is definitely yes. The US is the 4th largest country by area, the 3rd largest by population, and emits the 2nd largest volume of greenhouse gases of all nations across the globe. So China is the only country that beats us there. And this map here on the screen shows all greenhouse gas emissions, including carbon dioxide, which is the most common greenhouse gas, but also methane, nitrous oxide, HFCs, CFCs, so those are both common household refrigerants. And to accurately show all these different greenhouse gas emissions in one graphic, they're expressed in terms of carbon dioxide equivalents. So basically, each carbon dioxide equivalent is weighted by its global warming potential, where carbon dioxide is arbitrarily assigned a global warming potential of 1. So for example, if a gas has a potential of 10, then 1 kilogram of that gas would generate 10 times the warming effect as 1 kilogram of carbon dioxide. So that's kind of how you put all those different things together. Just so you have a frame of reference, in 2016, carbon dioxide made up about 3/4 of global greenhouse gas emissions, followed by methane at around 15%, and then nitrous oxides and refrigerants made up the remaining 10%. So this chart here measures only carbon dioxide emissions, or what we generally refer to as just carbon emissions now. It doesn't include any of those other greenhouse gases, but since carbon is the majority share, watching this more specific metric can still give a good picture of relative greenhouse gas emissions over time. So you can see here again that in 2022, the US was 2nd in carbon dioxide emissions globally by nation. And it's just crazy to look at how steep this increase has been in the past 50 to 100 years. So looking specifically at the US, we can see that our carbon emissions from fossil fuels peaked at around 6 billion tons in the early 2000s. And since then, we've actually slowly been making progress to decrease our emissions. So this is due in part to the different initiatives that are set out by the federal government and local governments. According to the current administration's environmental goals, this line here on the graph needs to be back to 0 by 2050. So that means we have 27 years to undo what's been done over the past 150 years, which is very daunting, but can seem more achievable if we break it down into adjustments by individual technology. So on that note, we'll turn away from global emission statistics and focus specifically on what we're here to talk about today, which is hot water. So water heating constitutes just under 20% of total energy consumption in US residential buildings. It's at 18% here. It's kind of interesting also to look at this broken down by housing type. So you can see that multifamily buildings, especially larger ones, have the highest percentage of use of energy used for water heating. So that last slide was water heating energy use broken down by housing type. This one shows water heating energy use broken down by fuel type, which is a critical piece of information when we're talking about decarbonization. We see, as you might expect, that electricity and natural gas have the majority share of the water heating load. However, in 2020, you can see that there's an encouraging statistic that electricity slightly beat out natural gas, and hopefully that trend will continue. So this does include both electric resistance heating and heat pump water heaters. And then just another sort of interesting thing to note is that single family homes still use gas more for their water heating, and multifamily and commercial buildings still use electricity more than other fuels for water heating. So all those previous slides were about the first why of water heating decarbonization, greenhouse gas emissions reductions, right? Now we're moving on to the second why, although they're all interrelated, because this technology increases efficiency. So the first thing to look at here is the uniform energy factor, or UEF. So this rating is determined using a first hour rating, which is the amount of hot water that the heater will supply per hour in gallons, starting with a tank full of hot water. So the rating varies among models depending on tank capacity, heat source, the size of the burner. We used to use the energy factor rather than the uniform energy factor. The UEF was developed so that we could more accurately compare gas and electric efficiencies. So the data in this table comes from the AHRI directory, which is freely available online and gives an accurate representation of the heating and cooling technology that's currently available on the market. So looking at this data, we can see a couple interesting patterns. Firstly, the most common water heater in residential settings, a gas storage water heater, is also the least efficient by quite a margin. So it's the most used by quite a margin and the least efficient by quite a margin. So, and then you can see if you can't get away from gas, then tankless is your best option. It will typically significantly increase your efficiency level beyond a gas storage water heater. Both types of electric resistance water heaters have increased efficiency over gas, and heat pump water heaters are the most efficient by a huge margin. You'll notice that all the other efficiency ratings are less than 1, and heat pump water heaters are able to break over that threshold, and we'll talk about why that is a bit later on. So our third why for water heating decarbonization is about saving money, which is what a lot of consumers care about the most. This is a graph produced by ACEEE last year, showing the life cycle costs for different types of water heating options. So this graph shows the incremental cost for replacing a gas system at the end of its current service life. The data points include approximately 3,000 homes, and this looks at the direct capital and energy costs to the homeowner over the life of the equipment. And this is based on national level data, so regional discrepancies in gas and electric costs is smoothed out to a certain degree. This graph does not show electric resistance storage or tankless, but besides that, you can see this roughly lines up with the previous slide. Electric heat pump water heater as the most efficient is also the least cost, and then you have gas tankless and gas storage. So just so we all know how to read these graphs, the lines in the middle of each one are medians, then the whiskers on the ends show sort of the extreme points, and then the dots are the individual outliers. And the costs in here are all in 2020 dollars. So here's a real life project example that demonstrates this trend. So using energy modeling software, we modeled the same house in 2 different ways, one with a heat pump water heater with an average efficiency, and one with an electric storage water heater with a very high efficiency. And the model did show about a $400 savings per year in annual energy costs when using a heat pump water heater compared to an electric storage system. So while the initial cost for a heat pump water heater is about 3 times the electric storage water heater cost, over its lifetime, it will save more than that difference in energy cost. However, It's worth noting that in some locations, the cost of electricity is so much higher than the cost of gas that an efficient gas water heater can sometimes still have a lower lifetime cost to the homeowner than an electric heat pump water heater. And this is a real problem, right? But as we move towards decarbonizing our electric grid, shifting our electricity production away from fossil fuels and towards renewable energy, hopefully we'll start to see a shift where electricity will become the more affordable option nationwide. And we already see this in places like Washington State, where the abundance of electricity produced with hydropower has made their electric costs very low. So hopefully we'll see that reflected across the nation. And then another item where we can have a bit of savings for ratepayers is while the energy cost savings can vary regionally based on local utility costs, there are rebates and tax incentives available both locally and nationally that can also offset the high cost of heat pump water heaters. So until 2032, there's a nationwide federal tax credit that covers up to 30% of your heat pump water heater installation or retrofit project. And then it's also worth looking into rebates and incentives available on a regional level. So these are pretty easy to look up. Lots of manufacturers have rebate searches on their sites. Energy Star also has one on their website. So this is just an example. I used one of these manufacturer search engines for Rochester, New York, which is where I am from. And they right now have 2 utilities that offer heat pump water heater rebates. And you can see that if you stack those with the federal rebates, then you can get quite a bit of money for your heat pump water heater incentives. So the last place that ratepayers can look for savings is by using load shifting. So this is related to heat pump water heaters because it's only possible with electric systems. So if you have a gas system, you can't really do this. So load shifting works by integrating a battery with your electric system. So this here is a very simple example. A battery is collecting energy from the grid during the night when it's cheaper, and then doesn't have to use energy from the grid during the day when it's more expensive. A lot of industrial buildings already take advantage of this cost differential by running night shifts at factories, things like that. But we can take advantage of it at home too, with the integration of a battery. You can also look to offsite batteries. Here's an example of an offsite battery energy storage complex that allows for the collection and storage of electricity and a release of that electricity at a predetermined time. So this is actually the largest energy storage system in Europe, and it was launched just this year. That's in the UK. All right, so now we're moving on to heat pump water heaters. We're going to start by learning more about the technology behind them. So for those of you unfamiliar with the technology, we saw before that heat pump water heaters can have UEFs well above 1, meaning that they give off more energy in the form of heat than they use in the form of electricity. They do this by transferring heat from the air into water stored in a tank using compression technology, basically the opposite of how a household refrigerator works. So simply put, they move heat rather than creating heat. So everybody stay with me here, but we're going to go back to high school chemistry for just a couple of slides to understand the underlying principles that make this technology possible. So there are 2 key concepts to understand. The first one is the ideal gas law, which is from a chemist in the 1830s, which for our purposes basically tells us that when a gas's pressure increases, so does its temperature. And the opposite is also true. When a gas's pressure decreases, its temperature does as well. The 3 variables in the box there, volume, amount of gas, and R, which is just a number that makes the equation work. It's the ideal gas constant. Those 3 stay pretty much constant in the system we're looking at, so they won't affect this pressure-temperature relationship. So based on this rule, if you create pressure changes in a gas, you'll create temperature changes as well. So that's the first key concept, pressure and temperature. The second key concept is that during phase changes, when a substance, in this case a refrigerant, switches from gas to liquid or liquid to gas, heat is released or absorbed. So if you think about it, that makes sense, right? You need a certain amount of energy to go into a substance to make it vaporize, like when you're boiling water. And you need a certain amount of energy to come out of a substance when you're turning it back to a liquid. So that means that a gas going to a liquid releases heat, and a liquid going to a gas absorbs heat. So when we put these 2 concepts together, we end up with heat pump technology. We're using the first concept to force phase changes in the refrigerant, and the second concept to collect the hot or cold air released during those phase changes. So let's look at this another way. This is a diagram of how the heat pump technology used in heat pump water heaters transfers heat from outside to inside using a refrigerant. So we're going to start on the bottom right side here. In our loop, we have a refrigerant that is a liquid. Imagine that it's colder than the outside air. As it passes through the outside air, it will warm up. In fact, because the refrigerant has such a low vaporization point, which is why it's called a refrigerant, it warms up enough in the outdoor air to turn into a gas. So next, the gas passes through a compressor. And as we saw before, this increase in pressure will result in an increase in temperature. So now we have a high pressure, high temperature gas. This high temperature gas passes through the water that it's heating, and it starts to cool down again because the water is colder than the gas, and it cools down enough that the gas turns back into a liquid. And when this happens, as we talked about before, energy is released in the form of heat, so heating up the water. Then the refrigerant, which is now a liquid, goes through an expansion valve, which brings down its temperature and its pressure so that the process can start all over again. So heat pumps can have an efficiency greater than 100% because when heating, heat is extracted from both the work put in, which is the electricity used to run the compressor, and the heat drawn out of the environment added together. So whereas other technology can only create heat from the energy put into the system, the electricity put into the system, heat pumps have two different sources of heat. And then when we start looking at how this system works when it's cold outside, which is everybody's question now, the compressor turns out to be the pinch point in the system in terms of outdoor temperature. So if the temperature of the vapor coming in is very, very low, the compressor has to increase the pressure in the system enough to be hotter than the water that you're trying to heat. So the colder the vapor is, basically the harder the compressor has to work, the more electricity the system uses, and the less efficient it becomes. So that was your crash course in the physics and chemistry behind heat pump technology. Hopefully everybody followed along, but now we're going to move along to different configurations of heat pump water heaters. So there's a few different ways to set up a heat pump water heater system, and they're most commonly sold as unitary systems, which is what we see on the left here. Out of these three configurations on the screen, the unitary obviously is the most similar to gas and electric resistant storage water heaters that we have now. In fact, some manufacturers are developing heat pump water heater models that can plug into 120 volt outlets. So the idea is that all the plumber has to do is connect the two water lines, and it's as simple as that. The split system design in the upper left there places the heat pump equipment outside and the hot water tank inside, which eliminates the noise and cold air concerns that sometimes come with heat pump water heaters, which we're going to talk about later. And then the third configuration here is just an example of what a central system might look like for a larger building. So this would be used by multifamily or commercial buildings for domestic hot water. These systems get increasingly complicated the larger they get, but there are a lot of current research and development activities focused on central systems that would be easier to implement in multifamily settings. So once you pick the configuration you want to use, the next task is sizing, right? This isn't really very different from sizing a typical gas or electric storage water heater. You use the first hour rating, which is visible on the water heater's energy guide label, and make sure that the rating can accommodate the peak hour demand. So in this example here, the peak load is around 8 a.m. during the week. So to enjoy your morning shower, the tank needs to store enough hot water to meet that need. Something to keep in mind is that the first hour rating for a heat pump water heater is a little lower than electric resistance for gas. So this means that when you're sizing for a heat pump water heater, the recommended tank size is typically larger than it would be for a gas or electric resistance water heater. So heat pump water heaters essentially take longer to heat water than those other technologies. So having a larger tank means that you won't run out of hot water and that the heat pump water heater won't need to switch to electric resistance mode. Many of them have this backup mode to provide the hot water you need. Another option besides using a larger tank is to let your heat pump water heater actually overheat your water. And then using a mixing valve, you can temper the water before it gets to your shower or your faucet. To illustrate that point, we have three energy guide labels here for different water heaters. The one on the left is a 55-gallon gas water heater, with a first hour rating of 91 gallons. In the middle is a heat pump water heater that has about the same tank size as the gas storage water heater, but has a much lower first hour rating. And then on the right, we have a heat pump water heater with a similar first hour rating to the gas water heater, but with a much larger tank. So just for reference, when we're talking about the sizing here, a 5-minute shower is estimated to use 10 to 15 gallons of water, depending on the water efficiency of your shower head. So next, we need to pick the right place to install our properly sized heat pump water heater. 3 things to consider when picking the best location are temperature, amount of space, and proximity to living space. So heat pump water heaters run the most efficiently in warm spaces with plenty of air volume. Looking at 4 different areas where a heat pump water heater could be located, here we see that the basement near the furnace, where it's warm and there's lots of space, is a great place to be, and it runs very efficiently. And then kind of the next best space, which is also very common, especially in multifamily situations, is the laundry room. So it's already warm and humid in here, which helps the heat pump water heater to run efficiently, but it can be lacking in air volume. The heat pump water heater will absorb the excess heat and moisture and keep the laundry room from having moisture issues as well. And then the next sort of option we've got here is an unconditioned attic. So here we have the opposite problem. There's a lot of space, but the temperature fluctuates quite a bit. And then we see that one of the worst places would be a bedroom closet, right? Because it's very close to living spaces. Being in conditioned space will help the equipment to run efficiently, but it also probably will bother the residents with noise and the cold air that it gives off. So aside from air source heat pump water heaters, which we've been talking about so far, there are also ground source heat pump water heaters. So just like ground source heat pumps for space conditioning, these systems take advantage of the relatively stable temperature of the ground once you go down a few feet below the frost line. These systems can be especially helpful in colder climates, where air source heat pump technology could be less efficient due to cold outdoor temperatures, as we talked about previously. So here on the screen are 3 different configurations of ground source heat pumps. On the left, we have horizontal loops, which require trenches at least 4 feet deep. So this on the left here is called the slinky method, because it kind of looks like a slinky, if you're familiar with that toy. And this allows more pipe in a shorter trench, which cuts down on installation costs. And then in the middle, we have vertical loops, which require much less land, but they're drilled about 100 to 400 feet deep. And they're connected with a horizontal pipe, which is basically the manifold. And that's placed in a trench, and then that's all connected to the heat pump in the building. And then the third layout we have here on the right side is a pond or a lake system. So this is actually the lowest cost option, where a supply line pipe is run underground from the building to the water and coiled into circles at least 8 feet under the surface to prevent freezing. So the main downside, though, of ground source is the cost, which can be much higher than for air source, although the upside for ground source is that it can be more efficient. So that was a crash course in heat pump water heaters. Now we're going to talk about a couple other relatively good options for improving your water heater's efficiency. One is tankless water heaters. So there are 2 options for tankless, gas and electric. These pictures on the screen here are from one of Newport's office buildings, which has 3 stories above grade and also a basement. It was built around 1930, all brick, super thick walls. The commercial office space for the business is on the 1st floor, and then the 2nd and 3rd floors have apartments. So this building originally had a gas boiler, a gas water heater located in the basement, and then a gas fireplace on the 2nd floor in one of the apartments. Last year, we had to replace the gas water heater. So this is a pretty common scenario for older buildings, especially in the Northeast, that your main source here for heating is gas. So we started looking at some different options. A heat pump water heater was crossed off the list because it was just too expensive, and distribution would have been really challenging because of the layout of the building and very slow. So it would have been an expensive solution for slow hot water. but we were also conscious of trying to be more environmentally friendly. So we started looking at these tankless options. And if you already have gas service and a gas water heater is your best option, then what you need to do is get a gas tankless, right? It is more expensive than the traditional gas water heater with storage, but it's so much more efficient, as we saw before. So unfortunately, for many retrofit situations like this one, that may be the best you can do. It's not complete decarbonization, but it does help quite a bit. Another option, which is less common than the tankless water heaters, is, at least in the US, is a solar-assisted heat pump water heater. So on the screen here, we have the cover photos for two different products. One is British, the other is Portuguese. And solar-assisted heat pump water heaters work by combining solar energy from thermal panels and heat pumps to produce heat. So there are all different configurations and types of solar collectors used with these systems. This is a real-life example of an installed solar-assisted heat pump water heater from the UK. So along with their solar-assisted air source heat pump water heater, they also used two additional air source heat pumps for heating and cooling in the home. So this was an all-electric home, completely fueled by heat pump technology. So these two on the screen, evacuated tube collectors and PV thermal or hybrid. These are the most common types of collectors used with solar-assisted water heating. Evacuated tube collectors are the most efficient collectors available and work well in most climates, including colder ones. So each evacuated tube is similar to a thermos in principle. A glass or a metal tube containing the water or refrigerant is surrounded by a larger glass tube, and then the space between them is a vacuum, so very little heat is lost from the fluid running through each tube. So in warmer climates, you can use water directly, so your water from your thermal tubes goes right into your water heater. It's been heated by the sun. But in colder climates, instead of using water, you would want to use a refrigerant because you don't want the fluid to freeze and then crack the collector if it's too cold outside. And these collectors actually can even work well in overcast conditions. And if you're using the right refrigerant, can operate in temperatures as low as -40 degrees Fahrenheit. Individual tubes can be replaced as needed, which does help with the cost effectiveness of this option because typically these systems are very expensive, but the ability to replace individual parts one at a time does help with that. You don't ever have to replace the whole thing at once typically. And then the next option is the PV thermal or hybrid. So these work well in warm and cold climates as well. And basically they combine PV solar cells and thermal panels. So the excess heat from the PV is transferred through the solar panel to the refrigerant. So the PV can also power the compressor as well, which makes this system very efficient too. Another interesting option is integrated space conditioning and water heating. So rather than a different heating technology, this is sort of a different configuration where you can get more efficiency out of the one system. So in this scenario, we can have a very large heat pump that basically generates both the home's heating and cooling and the hot water. So this means that you can have a larger heat pump, which can be much more efficient and require less maintenance. But then on the other hand, if it goes down, then everything goes down in your house. This is a real life example of one of those systems. So this is in Washington State, which is a relatively mild marine climate. The builder says that they love these systems. They do heating, cooling, and domestic hot water for about $30,000, which they say is about $10,000 less than local installers are doing for less efficient systems. So that's a pretty cool statistic. And the specific system in this house is a combined air to water heat pump for space and water heating. It's 50 gallons. You can see it back on the right side there, the cylindrical tank. And it's in a conditioned basement, and it does have electric tankless backup water heating in case the heat pump can't keep up during a cold snap or something like that. This is another example of a combined system. So this is by also a builder in Washington. So again, a more mild marine climate. but they use radiant heat for space heating. So in this situation, basically using the hot water produced by the water heater for both space heating and for water heating. So you can see the radiant heat tubes running through the floor there before the flooring's been put down. So we briefly touched on this before when we were talking about the best place to put heat pump water heaters, but here we'll talk about the challenges and opportunities for improvement that we have with heat pump water heaters. So this is kind of the most interesting section because this is what we're dealing with now and trying the things we need solutions for. So those challenges are noise, the cold air that they let off, which is their HVAC impact, maintenance problems, climate, and space. And then climate and space are definitely the biggest challenges of those 5. So all water heaters, right, have to expend more energy if the water coming into the tank is colder. So this is separate from heat pumps, which sometimes have challenges with cold climates. This is the water heater itself, because the water coming in is colder. So colder air temperatures in the winter make the ground with the water pipes in them colder, right? And then the water inside the pipe gets colder with a small delay. And then these colder groundwater temperatures pose a threat to the performance of heat pump water heaters in cold climates because the system has to heat colder water, requiring more work. But this issue might be less of a concern in warmer climates. So this graph here just shows the fluctuation in incoming water temperature across a season, a heating season. They also vary regionally. So heat pumps and heat pump water heaters typically work best in moderate climates. This map from the Building America Solutions Center shows the 5 general climate regions of the US. You can see that the southern half of the US and the West Coast are relatively mild, but a large portion of the US is cold and very cold. So new cold climate heat pump technologies are being developed. In fact, the Department of Energy currently has a cold climate heat pump challenge going on right now where manufacturers and researchers are working together to improve this technology. And then also another program that Newport Partners helps out with is the Zero Energy Ready Home program. And in that program, we do see installations of heat pumps and heat pump water heaters all over the country, regardless of climate. And so regardless of the climate, and particularly in cold climates, it's important to locate the heat pump water heater in conditioned space because most units need a temperature range of about 45 to 100 degrees, 120 degrees Fahrenheit for effective, efficient operation. So in single family homes, this isn't too hard. The water heater can be tucked into basements, crawl spaces, garages, attics, or their own closets that are away from the general living space. So in the Northeast, where it's cold and there are basements, a conditioned basement could be a good location. In the Pacific Northwest, where it's a little more mild, a garage could be ideal. In the Southeast, where often basements are not built, then garages or conditioned attics can work. But then location of heat pump water heaters is more of an issue in multifamily buildings where floor space is very valuable. So we've seen them in Southern California, places like that, outside in a mechanical closet on the balcony because the air temperature there is mild enough year round that the heat pump water heater can work effectively. So heat pump water heaters do need a decent amount of air volume to work efficiently. If your room is less than about 700 cubic feet, you probably need some workarounds. And this air volume can vary, and you can see the manufacturer instructions for each unit will typically have a recommendation for the amount of air volume needed. And that recommendation is typically what's needed for the heat pump water heater to run at the maximum advertised efficiency, so the maximum UEF that they've got there. So there are 3 options. One is to louver your door, so basically have a door with slats in it, and this is pretty common in apartment buildings. And that way the air volume in your small mechanical closet combines with the air volume in the rest of the area, and that gives you enough air volume to work with. And then another option would be to do just one duct, so an inlet or an outlet duct for the equipment, and then also have an air gap under the door. And then a third option would be to duct both the inlet and the outlet. So in this situation, you don't need any additional ventilation because you're sending all the cold air out and you're bringing all the conditioned air volume in that you might need. This is an example of how two of those space-saving options might be integrated into a 2-unit apartment setup. So you can see at the top there, there's a louver door in Unit A's living room, and then in Unit B, we've got a ducted to the outside configuration in the kitchen area. So another issue is noise. So heat pump water heaters can be noisy, which is an obvious issue, especially within multifamily units or in single family homes that don't have basements or garages. All the units typically can be switched to an electric resistance backup mode. So that eliminates the noise entirely, but kind of defeats the purpose, right? You could just have an electric resistance water heater at that point. So the units currently are not rated for noise, although some units do show like a decibel rating. And there has been some discussion around a standard for this issue. So it's been thought about a lot through the industry. A lot of the time, the noise is actually vibration. So if your heat pump water heater tank is by a stud, then that noise can show up other places in your house. So some solutions to that are you could put vibration earthquake straps or rubber pads against the basin walls, and that can alleviate some of the noise. So another challenge is maintenance, right? As with all equipment, heat pump water heaters need maintenance and filter cleaning or filter replacement according to manufacturer specifications in order to run efficiently and as they're supposed to. And this can range from once a month to every 6 months. But in a multifamily situation, that means that you need access to each apartment on a regular basis. And this can be tough if tenants and renters are not responsible for maintenance. The property manager has to make sure that they have regular access. They might worry about bothering their tenants. So that can be a big challenge for multifamily settings. So this home case study was designed to have an exhaust duct in the utility laundry room for any excessive moisture, and also to help better circulate the cool air that's inherent with a heat pump water heater. So as such, the unit stays in heat pump mode for most of the year without causing any discomfort. And this contractor told us that in another home that they built, they have a heat pump water heater in an unvented utility room. And the cooler air creates a discomfort issue in the colder months for the homeowner. So it's switched over to electric only for about half the year, 6 months out of the year. And that's been going on since 2015. But in this newer home shown here, which has been occupied since 2021, there have been no complaints for the homeowner, and the unit has been running in heat pump mode year round. So that just goes to show that venting can be a very effective way to make these heat pump water heaters work well in small spaces. So this slide here is the same project. This is just a close-up of the equipment used in that project. So it was a 50-gallon Energy Star rated Rheem Performance Platinum hybrid heat pump water heater. And it was located in the laundry utility room here. For multifamily buildings, there are 2 basic configuration options for air source heat pump water heaters. We have individual water heaters, so that's a heat pump water heater in every unit. And then we have central systems, which is one sort of large system combined that provides water to the whole building. So this is an example of a centralized heat pump water heater design that uses individual heat pump water heaters. So this is kind of a creative example of the individual heat pump water heater configuration. So this is one heat pump water heater serving 4 different units. So the greatest benefit to this, and this only really works if your units are quite small, is the reduced cost, right? So it's reduced first cost for the equipment, reduced plumbing costs, reduced maintenance and replacement costs, since there's only 1 unit for the 4 units, one equipment unit for the 4 units. But then you have disadvantages like the increased likelihood of running out of water. Failures will impact more people. And there's probably going to be a lower efficiency on your heat pump water heater due to all the hot water loads that might happen at the same time. So a Seattle research firm, a federal utility agency, and manufacturers have been working together for the last 10 years on this kind of specific project to develop new and easy to install commercial heat pump water heating systems for multifamily buildings. So this has been a big area of development recently because we don't really have too many good solutions right now, especially in the United States. So this is a system that includes a Mitsubishi heat pump on its own, and then primary storage tanks, which are plumbed in parallel. It's got a temperature maintenance system that uses some electric resistance tanks that were reused from the old system, but they're just used as storage. And then another cool thing is that the heat pump uses carbon dioxide as the refrigerant, which is a natural refrigerant with a global warming potential of 1. So it's also a great candidate for outdoor installations in cooler climates, especially because the operating temperatures or the operating pressure, for carbon dioxide as a refrigerant can be very high. So often, due to safety concerns, it's best to have the units outside. So this is another good example of a central system. So this is a building that is mixed use. It's in New Paltz, New York. So another colder climate example. It has 46 apartment units, a first floor retail space of about 8,000 square feet. And it has 5 affordable units as well, which is pretty cool. So this project uses a geothermal, they call it, but it's really ground source heat pump system that uses wells. And the wells are confined to the building's own footprint, which means that they did deep vertical wells rather than the flat loop systems. So this system has 4 tanks that are plumbed together, just like the previous example. And in this situation, they've got tanks 1 and 2 are kind of preheating the water, and then tanks 3 and 4 take that water all the way to full domestic hot water temperature as needed. And so this system actually combines water heating, space heating, and air conditioning all together into one heat management system by using water as the heat transfer medium throughout the building. So that's similar to if you were doing a combined system and you had radiant heat with your domestic hot water all coming from the same heat pump water heater. And then so during the cooling season, though, the unit heat pumps functioning as air conditioners put the heat into the water loop where it can then be used by the heat pump water heater so that the excess rejected heat can go into heating the domestic hot water. So it's a cool kind of circular system that's going on there. And this is actually the second multifamily building in New York State to use this strategy. And the builder has said it's 4 times bigger than the first building that used this strategy. So that demonstrates the scalability, which is really what we're looking for out of these systems. Installers really need sort of a set of technology that can be implemented all at once or in a very specific set of pieces in order to make this more widely available on the market, because right now, for the most part, there's sort of specific installations designed uniquely for each different situation, and it's not really the same across the board, which makes it challenging to do on a larger scale throughout the market. So these are some various manufacturers that are already selling heat pump water heaters, and they're all working to innovate and improve the technology. So they've all been present on one of DOE's manufacturer roundtables. So there they kind of share their most recent innovations and what they're currently working on to improve the technology. So on the left, we have Rheem. They're the group that's working on the 120 volt model that plugs in so that it can easily replace an old water heater. And so far, it looks like they've done this by kind of dropping the electric resistance back up to greatly decrease the electric load. So if you're in a place where that won't be an issue, a warmer climate, then that would be okay, but might not work so well for colder climates. So that's just something to really read between the lines on when you're considering purchasing one of those, but we'll see what they come up with in the future. And then we've got Eco 2, which is using carbon dioxide for the refrigerant. Again, the global warming potential of carbon dioxide is 1. So it produces the hot water in the heat pump and then pipes it to the tank. And like we said before, the heat pump lives outside for safety reasons because of the high operating pressures of carbon dioxide as a refrigerant. And then A.O. Smith is focusing on the ease of installation. There's no connections on the back or side. They've made a zero clearance design, and then the connections for the water on the top or front. So they're trying to make it as easy as possible for a plumber to just set this in place and then hook it up and have it ready to go. Bradford White is also thinking about ease and quality of installation. On all of the units that they sell, they have a QR code with installation instructions for install, QA, and to just help manufacture or to help contractors out who may not be familiar with the technology. And then we've got Ice Air, which is working on new cold climate heat pump water heaters. I believe they're part of the DOE Cold Climate Challenge, or they are with one of their partners. So they're out of Mount Vernon, New York, and their heat pump water heater series is tested to -13 degrees Fahrenheit. So if your basement gets that cold, then this is the product for you. And it provides hot water even when it's very, very cold outside. And then Energy Star through the EPA also has, currently they have cold climate rated heat pumps, but in the future they're looking towards developing a standard also for heat pump water heaters. So heat pump water heaters are a relatively new and evolving technology. There's lots of challenges that we face. Many of those are still ongoing questions that we don't have answers to. So things like, where do I put it if the unit doesn't have a basement or garage? How do I keep it from negatively affecting the homeowner? In multifamily settings, how do I keep the tenants from just switching it into electric resistance mode? And then I just bought a ton of really expensive water heaters that are just acting as electric resistance water heaters, which have been much cheaper. And we've heard a couple of projects where that has happened, and there's not really anything that the building owner can do because it's the tenants living in the spaces. And then also, will the consumers accept these challenges? Like, will they accept the noise and the cool air? This is the reason that those tenants did switch them into electric resistance mode. Thinking about the return on investment, right? Especially in places where utility bills can be so different between gas and electric, and where a very efficient heat pump water heater might still be too expensive over the span of its 10 or 15-year life because electric rates are so much higher than gas rates. And then there's also hybrid heat pump water heaters, where rather than having a electric resistance backup, they can also use gas. So it's kind of like a dual fuel heat pump in that when you can monitor via some kind of a computer program when the electric rates are higher or lower, the gas rates are higher or lower, and then use that fuel based on, and then it has the ability to switch between fuels based on the expense or based on the outside temperature. And yeah, so it's just continuing to consider how heat pump water heaters and space heating can be best integrated together to form more cohesive systems, more efficient systems. So feel free, if you have any ideas for how to solve these problems, to contact us and let us know. And then there's also lots of resources out there. So EPA every year has a heat pump water heater day. So you can see on the right there is Mr. Heat Pump Water Heater from last year's Heat Pump Water Heater Day. We've also got the Advanced Water Heating Initiative, which has key groups that target residential, commercial, and controls groups. So the controls groups would be working on things like those fuel switching programs. And then again, Energy Star has a whole heat pump water heater education page. They've got a manufacturer action council providing training, marketing, sales, engagement, things like that. So that's all I have at the moment on heat pump water heaters and water heating technologies. So if we have any questions, we could go on and answer some of those.
Well, Sarah, that was the best explanation of how the second law of thermodynamics works in relation to heat pumps that I've ever heard. And I've probably sat through 12 heat pump water heater training courses. So congratulations on simplifying that for everyone. Some questions around we hear that GE is coming out with a heat pump water heater unit, and then your thoughts on the Sandon unit, I think, which also is a CO2 split unit.
Mm-hmm. So I'm not familiar with the GE unit. I can't actually say that I know too much about the Sandon unit either. Is that a commercial one, like for
Uh,
essential, or is it a like a
yeah, my
low?
understanding is this, the sanding can be used for residential, is CO2 driven. The condenser is outside. I think it would be very similar to the Eco 2 model that you talked about. And I know we've had some builders using that with some good success. And then actually EBA is part of the Advanced Water Heater Initiative. And I
Mhm.
know in being part of that, that GE will have a new line of heat pump water heaters coming out very shortly. So, watch this space for it. But probably the most intriguing part of it is I think it seems to us here in North America that a lot of these great heat pump water heater solutions may already exist in Europe or Southeast Asia.
Yeah.
And is it as simple as bringing that technology over, or, how do we all help accelerate the adoption of this technology in our market?
Yeah, so that's a tough one. It would be nice if we could just say, hey, look, France did it well, let's do that. But in reality, there's a lot of barriers here. One of them is that we have very different code regulations about refrigerants. So especially with these carbon dioxide refrigerant systems, they're um, often defined as dangerous because of the high operating pressures. And then with other low global warming potential refrigerants, they are toxic, things like that. And in the rest of the world, people have proved that you can use them safely, but we're just a step behind here in the US with having our codes come up to speed. And even for heat pump water heaters themselves, there's not even a standard for refrigerants in those settings. So there's great ideas, and it seems like people have great solutions that they've already been using, but in the US it seems like we're a step behind, and a lot of the systems we want to use we kind of have to import and then cobble together on our own, especially for central systems. So we have a ways to go, but it's great that we have these other examples that we can look to.
Great, thank you. Question that came in is, do you see the electric tankless water heater technology as an efficient alternative to traditional tanks?
So if you're talking about a traditional gas tank, then maybe. If you're talking about a traditional electric resistance tank, then yes. So typically, you can see between a storage tank and a tankless that the tankless is really going to be more efficient almost 100% of the time. But it does depend if you're switching between gas and electric, then that can change a little bit.
Yeah, absolutely. And I think there's kind of that good, better, best, right? I think
Mhm.
depending where you are in North America, you may decide that you want to do a hybrid water
Mhm.
heater and use natural gas as your backup, maybe from a resiliency perspective, but be
Mhm.
ready for. I think that's kind of as you look at Zero Energy Ready Home program or the Energy Star Next Gen program, I think what they're telling us as an industry is be ready, be able to future proof that installation, be able to switch over as the heat pumps get better and better and the technology evolves. But there might be kind of this good, better, best continuum right now that people want to take a look at, right?
Yeah,
And
exactly.
then I think what I hear you saying, Sarah, is once you decide to maybe go to heat pump water heater, there's some thought that needs to be done. And I think that's what I hear from the Advanced Water Heating Initiative calls with a lot of builders across the United States is we had to be thoughtful about where we put it.
Mhm.
I can't just put it underneath the primary bedroom in the basement. I'm going to put it over here. The garage might be a great place. Perhaps the laundry mudroom is a really good place. And we can capture some of that heat recapture from the dryer that goes to the water heater and does a louvered door. So I think there's some thought that has to happen, but a lot of people are currently looking at that. There's a lot of brain horsepower that's looking at this. And again, I think with EBA and with Newport partners, and of course our partners at DOE and Energy Star, we want to continue to share those best practices with all of you. So
Yeah, for sure. And speaking back to your point about heat pump water heater readiness, that is currently a requirement in our new version of the Zero Energy Ready Home program. But something that's actually still in there is that you're exempt from that if you're using any kind of a tankless water heater. And we don't restrict it to electric, even though electric can be decarbonized, because gas tankless is so much more efficient
That's
than
right.
electric tankless right now. So yeah, it's a balancing act of
Yeah.
Using as little gas as you can versus if your electricity isn't really decarbonized, then is there any benefit? So yeah, it's always
Great.
balancing those things.
Yeah. Well, I want to thank you on behalf of EBA and all of our attendees today for an incredibly thoughtful, informative presentation. And as always, it's our pleasure to have Newport partners join us in the EBA webinar podcast series. So Sarah, thanks so much.
Yeah, thank you for having me.
All right. Thanks, everyone.